Okay. The next objective we have is to define the pH. And the pH is simply a negative log of the hydrogen ion concentration. A negative log of the hydrogen ion concentration. And we're going to show you, the objective says, given any hydrogen ion concentration, determine the pH and vice versa. So we're going to show you some tricks here before we get into determining the pH. Some useful conversions that you should know. I hope you can see that. First thing, what we don't have up here, and I assume you all know, is that the log of 10 is 1, the log of 100 is 2, the log of 1,000 is 3, and so on. And that the log of 1 is 0. You have to learn that. The log of 1 is 0. The next thing I want, you probably all know that. The next thing I want you to learn and memorize is that the log of 2 is 0.3. Because if you know that, if you know this, that the log of 2 is 0.3, you can estimate a lot of logarithms. If somebody says, take the log of this number, you can estimate it. Because if they say, if you know that the log of 2 is 0.3, and don't use all these numbers, in biology, you can't go past two significant numbers for, there's not much you can go past two significant figures with. And for the log of 2, 0.3 is fine, 0.3. You got to remember that the log of xy is equal to the log of x plus the log of y. Okay, so if somebody tells you this information and they give you this information and then they say, what's the log of 4? Well, you can estimate it. You can say, okay, I know that the log of 4 is the log of 2 times 2, and that's equal to the log of 2 plus the log of 2. And the log of 2 is 0.3, and the log of this is 0.3. I combine them, I get 0.6. I can go on and say the log of 8 is the log of 2 plus the log of 2 plus the log of 2. That's 0.3 plus 0.3 plus 0.3, which is 0.9. So I can make a guess. If I only know that one number, I can make a pretty good guess for numbers 2, 4, and 8, and I can just guess about what's in between. Another thing that you should keep in mind, because you don't want to be, if you're like me anyway, some of you are mathematicians, you won't have to worry about this a bit, but for me, I hate negative logs. So I don't want to be taking the logarithm of negative numbers. So anytime a number, or ratios, or decimals, so anytime I make sure that the big number's on top. Okay. Remember that the log of x is equal to a minus the log of 1 over x. We're saying the same thing here. The log of x over y is equal to a minus the log of y over x. So if you're looking, somebody says, take the log of 0.5. Well, you know that's a log of a half. I wouldn't mess with that. What I would do is say it's a minus the log of 2. And I know what the log of 2 is up there. It's 0.3. So I know that this value, a minus the log of 0.5, is really a minus 0.3. That's the log of it. Now, armed with those simple facts, we're going to go on here and start determining things. We're going to determine the pH of a water solution. Now, in a water solution, we know, because we know about the Kw, the ion product of water, we know that in pure water, we have 1 times 10 to the minus 7th molar hydrogen ion and 1 times 10 to the minus 7th hydroxide. We don't need the hydroxide for this. We're just interested in the hydrogen. And we want to take a minus a log of the hydrogen ion concentration. That's the definition of pH. That's a minus a log of 1 times 10 to the minus 7th. And since the log of A times B is equal to the log of A plus the log of B, we can say that this is equal to a minus the log of 1. And we can say it's plus a minus the log of 10 to the minus 7th. Well, the log of 1 is 0. So this term drops out. the log of 10 to the minus 7th is a minus 7. And a minus 7 times a minus gives you 7. So the pH of pure water is 7. And we're going to do a couple more here. We're going to do the pH of blood. It's not neutral. It's at 7.4. In fact, it's 40 nanomolars is what it is. Okay. We're going to determine the blood pH of different blood samples. Here's the first one here. Okay. We know ahead of time that our blood is pH 7.4, but we're going to determine it anyway. It turns out that the hydrogen ion concentration in blood is 40 nanomolar. 40 times 10 to the minus 9th, and that's the same thing as 4 times 10 to the minus 8th. We're determining the pH of it is equal to the minus the log of the hydrogen ion concentration equals a minus the log of 40 times 10 to the minus 9th. That's equal to a minus the log of 4 times 10 to the minus 8th. That's equal to a minus the log of 4 from this term, and then a minus the log of 10 to the minus 8th. What's this figure? Log of 4, well, the log of 2 is 0.3, so that's 0.3 plus 0.3. This would be 0.6. The log of 4 is 0.6. It's a minus in front of there, so that's a minus 0.6. The log of 10 to the minus 8th is 8, a minus 8, excuse me, but a minus times a minus is a plus, so you get a plus 8. A plus 8 and a minus 0.6, when you combine them, you get a pH of 7.4. Now, for fun, we're going to double the hydrogen ion concentration. We're going to make the solution more acid. Let's say we added hydrochloric acid to this, just enough, so that we made it twice as acid as it was before. So instead of 40 nanomolar, we now have 80 nanomolar. The pH equals a minus the log of the hydrogen ion concentration equals a minus the log of 80 times 10 to the minus 9th. And that's the same thing as a minus the log of 8 times 10 to the minus 8th. That's a minus the log of 8. Now, the log of 8 would be the log of 2 times 2 times 2, which would be 0.3 plus 0.3 plus 0.3. That gives you a minus 0.9 there. A log of 10 to the minus 8th would be a minus 8 times a minus 1, gives you 8, so it's 7.1. So we double the hydrogen ion concentration, and the pH went from 7.4 to 7.1. We'll get back to this, but you should see something there. You should see that whenever you double a number, when you multiply by 2 or divide by 2 in logarithms, you'll always change the value by 0.3. This has gone from 7.4 to 7.1. That's because we double the hydrogen ions. Doubling changes the value by 0.3. Now, what we're going to do here in this last one is we're going to have the hydrogen ions. We're going to make the solution more basic. Let's say we added a little sodium hydroxide to the solution. Now, the concentration of hydrogen ion is going to be 20 times 10 to the minus 9th. And we go through the same process here. We've got the log of hydrogen ion, 20 times 10 to the minus 9th. That's equal to a minus the log of 2 times 10 to the minus 8th. I'm sorry, that bracket should come down here. That's equal to the minus the log of 2 minus the log of 10 to the minus 8th. That's equal to a minus 0.3, because that's a log of 2. And the log of minus the log of a minus 8 is 8. You combine them at 7.7. Look what happened. Look what the difference was from the value of 7.4 up there. When we have the hydrogen ion concentration, When we have the hydrogen ion concentration, it changed from another factor of 0.3. It went from 7.4 to 7.3. So you will learn that when a person's blood goes from 7.4 to 7.1, that's a pretty dramatic change in the blood value of the pH. But in real terms, what you've done is double the amount of hydrogen ion in the blood. And if it goes from 7.4 up to 7.7 in real thought waves, what it's done is halve the hydrogen ion concentration. So it's helpful. Learn that the log of 2 is 0.3. Remember that you have to remember the simple logarithms. 10 to the 1 is 1, 10 to the 2 is 2, 10 to the minus 2 is a minus 2. And remember that if you change the sign in front of the logarithm, you can invert the denominator and the numerator, and you'll be all right.